Your cache is amazing, until it runs out of memory. Or crashes. What then? Today we find out. Welcome to part 3 of caching. The final part. Today, distributed caching. Quick refresh. In part 1, why caches exist. Hit, miss, hierarchy. In part 2, the strategies and policies. Cache aside, write through, write back, eviction. Today, what happens when a single cache server isn't enough? 2 reasons one cache server stops being enough. 1. Memory. Cache servers hold data in RAM. RAM is expensive and finite. A single machine maxes out around a terabyte. Most apps need more. 2. Failure. If your one cache server crashes, every request goes to the database. Your DB chokes. Your app dies. The solution is the same as for application servers. Run many. First idea. Modulo hashing. 3 cache servers. For each key, compute hash of key, modulo 3. Key 1 to server 0. Key 2 to server 1. Key 3 to server 2. Key 4 back to server 0. Simple. Works great. Until you need to add a 4th server. Now you compute hash mod 4. Almost every key gets remapped. Cache hit ratio collapses to nearly 0 overnight. Every lookup misses. Every request slams the database. Your melts. Solution. Consistent hashing. Picture a ring of numbers. 0 at the top. Maximum hash value just before 0. Each cache server gets placed at some position on this ring. Server A at 100. Server B at 500. Server C at 900. For each key, you hash it and find its position on the ring. Then walk clockwise to the next server. That server owns this key. Beautiful property. When you add a 4th server, only the keys between the previous server and the new one get remapped. Roughly 1/4 of your keys, not all of them. When you remove a server, its keys get redistributed to its neighbor. Everyone else is unaffected. Consistent hashing is what Redis cluster, Cassandra, and DynamoDB all use under the hood. 1 refinement. Virtual nodes. With 3 servers at 3 positions, distribution can be uneven. One server gets a much bigger slice. Fix. Place each physical server at many positions on the ring. 100 each. Slices average out. Each server handles roughly the same share. And when a server fails, its 100 positions get spread across all remaining servers, not dumped on one neighbor. Now a different problem. The thundering herd. A popular cache entry expires. The homepage of a viral tweet. 1,000 requests land in the same millisecond. They all check the cache. They all miss. 1,000 requests simultaneously hit the database for the same data. The DB, which was fine when cache was helping, suddenly takes 1,000 times the load. Latency spikes. Or the database crashes. The problem isn't the cache miss. It's that 1,000 misses happened at the same moment. 2 common mitigations. First, lock and fetch. When the cache misses, the first request acquires a lock. Other requests wait. The first request fetches, fills the cache, releases. The waiters then read from the warm cache. Second, stale-while-revalidate. The cache returns the expired entry to readers while asynchronously fetching a fresh copy. Users get slightly stale data but nobody waits, and the database sees one request, not 1,000. Let's land this in real tools. Redis, the most popular in-memory cache. Complex data types, persistence, replication, clustering. Works as both a cache and a key-value database. Has features for solving the herd problem. Memcached, simpler. Just key-value pairs, no persistence, no replication. Faster for pure caching workloads. Less to think about, less to break. CDN Cloudflare, CloudFront, Fastly. Distributed caches for HTTP responses. Cache by URL, support TTL, run in dozens of cities globally. All three use consistent hashing under the hood. When this comes up in a system design interview, expect probes like these. Probe 1. How would you scale a cache to handle a petabyte of data? Answer. Consistent hashing across many cache nodes. Virtual nodes for even distribution. Probe 2. What happens when a cache node fails in a consistent hashing setup? Answer. Only the keys it owned get redistributed to neighbors. The rest of the cache continues unaffected. Probe 3. A hot cache key expires and your database is getting hammered. What do you do? Answer. Implement lock and fetch or stale-while-revalidate to prevent the thundering herd. Probe 4. When would you use Memcached over Redis? Answer. When you need a pure cache. No persistence. Simpler operations. Faster lookups. That's the caching playlist. Part 1. The why. Part 2. Part 2. Strategies and policies. Part 3. Distributed caching. Next up in the system design fundamentals, we tackle databases. SQL versus NoSQL. Indexes. Acid and base. Replication. Sharding. Subscribe so you don't miss it.